In this video, we will define the derivative of a function at a point. But first, we will once more review the idea that the gradient of a line drawn tangent to the function at some point can be determined using a secant line which passes through that point. Way back in the first video on limits, we had posed this problem. I had intended to address this in the last video of that series, but decided to look at a problem with easier algebra. The algebra involved in this problem is not all that difficult. Unfortunately, too often students enter calculus courses without sufficient skill in algebra, then accuse calculus of being very difficult. Calculus per se is not that hard. They're very simple ideas that just take a little while perhaps to become accustomed to, because maybe it's something you haven't thought about before. But once you understand these ideas, implementing them really requires skill in algebra. So here's the function, and we want to find the gradient of this tangent line drawn here. Well, what we do is draw a secant line, and we simply say, well, the gradient of this tangent line is going to be equal to the gradient of this secant line as h approaches 0. So the rise is simply the difference in the y coordinates, f of 0.5 plus h, minus f of 0.5. So here, f of 0.5 is already shown, it's 3. And of course, we have this distance here, h. And we want to see then what this expression approaches as h approaches 0. Here we have the gradient of the secant line, and we want to know what value this approaches as h approaches 0, because that will give us the gradient of this line drawn tangent here. So what is f of 0.5 plus h? Well, here is f of x, and all you have to do is take this expression here and replace this x with 0.5 plus h. So take your time and do this. It's not that hard. Just take away this x, and in place of this x put 0.5 plus h, and you will see that you'll get this. In other words, this down here was x, and now it's 0.5 plus h. f of 0.5, well, we know it's 3, but for now, let's just write it out this way. Wherever I see an x, I put what? 0.5. So then we get this. From this point on, then it's just a matter of algebraic manipulation. So first, I get rid of these parentheses, and I find that 5 minus 5 is 0, leaving me with just this, and plus 1 over 0.5. And then I find common denominator here, and so then I have minus 0.5 here, and 0.5 plus h here. Once again, if you find this very, very difficult, you really need to go and get your algebra together. Go and do some intermediate algebra, and that should give you enough skill to do this. Preferably a college algebra course, but I think something like this you should be able to do this at the end of an intermediate algebra. So you're just finding common denominator. It's the same thing you learned way back in primary school when you're adding fractions. So this then simplifies. Notice we have minus 0.5 plus 0.5. That leaves us with just h, and then of course h divided by h is 1, leaving us with just what? 1 over 0.5 times 0.5 plus h. As h approaches 0, this expression then approaches 1 over 0.5 squared, which is 4. So this means that the gradient of this line drawn tangent to this function at x equals 0.5 is 4. That's the gradient of this line. This is the first derivative, or simply the derivative of this function at x equals 0.5. So let's say that again. The derivative of this function when x is equal to 0.5 is 4. In other words, the derivative at a point is simply the gradient. Now, to get this result involved a little bit of work, and well, we have a little problem here. Suppose we now wanted to find the gradient of a line drawn tangent at x equal 1, or at x equal 0.8, or at x equal 1.8. Well, every time we wanted to do this, we would have to go through this entire process again. So as you can imagine, that becomes a bit tedious. The good news is there is a way to get around that, and that's where we're heading. Here we have the function f of x equal 4x squared, and we want to know the gradient of the tangent line when x is equal to 3. So here the point is 336. We know that the gradient of the tangent line is going to be equal to the value that the gradient of the secant line approaches as h approaches 0. m is the gradient of this line drawn tangent here, and it's going to be equal to the limit as h approaches 0 of the gradient of the secant line. So once again, we have to get these values, f of 3 plus h. Well, wherever there is an x, we put 3 plus h. And then it's minus f of 3. That gives us the rise here. We know that f of 3 is 36, but let's do it this way. We put 3 where the x is, 4 times 3 squared. And then we expand this out, and so that gives us what we have here. This is 36. We expand again, and we get this expression, and now we see that 36 minus 36 gives us 0, leaving us with 24h plus 4h squared. We divide out by h, and we get the limit as h approaches 0 of 24 plus 4h, which of course is going to be 24. So the gradient of this tangent line is 24. So once again, even though the algebra here isn't so hard, we see that we would have to go through all of this whenever we wanted to find the gradient at a different point. So if I wanted to know the gradient of this function at x equal 2, at x equal 4, at x equal 28, I would have to go through all of this. So keep this in mind. Let's now formally define what we mean by the derivative of a function at a point. If you have some function f of x, and you have some point in that function, a, so x is equal to a here, a, f of a. So remember, this gives us the y value. The derivative at the point where x is equal to a is going to be written as f prime of a. So note, f prime of a is the derivative of the function at x equal a. Now this is going to be equal to the limit as h approaches 0 of this expression. Remember, this expression represents the gradient of the secant line, where this is the rise and this is the run. The rise is a change in the y values. So that's f of a plus h, and this is then f of a. And of course down here we have the run, which is simply h. And so this limit gives us f prime of a, the derivative of the function at x equal a. Now there is a drawback to this approach, and that is that for every value of a, you have to go through this entire process. So what we want to do is, instead of finding f prime of a, what we want to do is find another function f prime of x. So that once we have this function f prime of x, to find the gradient at any point in this function, we simply substitute the corresponding value of a into this function and get that gradient. In other words, this will be what is sometimes called the gradient function. Okay, so bye for now.